Hi to everybody. Welcome to the AGN Tourneys 2021. Still waiting for the Renaissance. So as you know, AGN 14, which is the workshop of the Italian AGN community, has been postponed twice. And it was supposed to take place in Florence in 2020. Now it's planned to be still in Florence, but in 2022. And it will be organized by INAF, Osservatorio di Arcetri, and University of Florence. Now, 1 year ago, we proposed a series of talks with a particular format. Some of you already know this format is loosely, somehow inspired by the medieval tourneys with two opponents proposing their view on a specific topic. And of course, with the entire community actively participating to this challenge. Now, given the success of the first edition, we propose again this year, this second edition. The aim is to strengthen the link among the scientific community working on AGN science. And as you can see, the program has not been conceived to cover uniformly the topics of AGN. It actually, the program is a collection of topics that are supposed to be very interesting and selected to be particularly stimulating and particularly relevant for the scientific community. So please also note, there's another point. I also know that the schedule is not regular. We have two tourneys in the morning at 11 a.m., 4 tourneys at 3 p.m. And in addition, one day, November 9, we have 2 tourneys on the same day. And at the end of the tourneys 2021, so the last tourney on November 10, we'll announce the dates of AGN 14 of the meeting that will take place finally in Florence in 2022. So today, Francesca Panessa is the chair of the first tourney, and then please, Francesca, let's start the tourneys 2021.
Okay, so good morning, everybody. I have the pleasure to introduce this first tourney. And our first speaker is Matteo Guainazzi. Matteo has been traveling a lot, so it's difficult to summarize all his scientific experience. He has in common with Giovanni that both of them got their PhD in at La Sapienza University in Rome. And then Matteo went to Japan as a visiting scientist, worked for Beppo Sachs in Rome, and then he moved to ESTEC in Madrid, having different roles within the XMM Newton activity. Recently, he also went to Japan again as a South astronomer to work to the Itomi project. And now he's a study scientist of the ESA Athena mission in Noordwijk. And today he will start the session of talking about changing look AGN. So I leave you the speech. Matteo.
Thank you, Francesca. I guess that you will shout if you don't see my presentation, if you don't hear me, and if you don't see the presentation mode.
We see the presentation mode.
So the right one or the good one?
No, the wrong one. Yes, all the presentation mode. Yeah.
What now? Now is better. Okay, thank you. So thanks for the invitation. And in preparing the first challenge of this tourney, I have, of course, asked for the help of some real expert in the field, at least a real expert in the field of medieval challenges. So first of all, let me make a clarification of nomenclature. Most of my talk will be on changing look AGN, and changing look AGN is a term that was originally used to identify a small subset of phenomena of state transition measured in X-rays. There is a small number of objects in the sky, a small number of AGN, that show in X-ray a transition between a transmission and the reflection-dominated spectral state. And while traditionally these states are associated with different degrees of obscuration along the line of sight, already in a paper where we, with Giorgio and Roberto, introduced the term changing look, half jokingly, we already put forward the idea that this phenomenon was actually the signature of a temporary switch off of the nuclear radiation, although at that time we didn't delve too much on the possible mechanism. Now, later, many of these X-ray changing look AGN were shown to be due to occultation events. And there was even later, several years later, a decade later, a systematic study looking at 230 years of light curves with XTE, X-ray light curves, showing that this kind of changing look transitions in the X-rays are actually relatively common. They happen around 10% in the life of a type 2, X-ray type 2, so obscured AGN. But more or less 10 years later, more or less simultaneously to the XTE study, the term changing look that had become a little bit of an enter into oblivion was actually resurrected to identify a similar but actually qualitatively different kind of phenomenology. So when we talk of changing look AGN or changing look quasars today, we refer to quasars where we observe on time scales that are typical of the order of a few years, the disappearance or the reappearance of broad optical lines. And the first example of this revamped definition of optical defined changing look AGN is a Sloan object that was published a few years ago by the group of La Massa, where comparing spectroscopic optical observations separated by 9 years, the disappearance of broad H beta and H alpha line was observed. And this was coming together with a decrease by 1 magnitude in the continuum G band. Now, for this specific object, X-ray spectroscopy, time resolved X-space spectroscopy was available and actually showed that the disappearance of the broad optical lines were associated with dimmed X-ray spectra without significant change in the spectral shape, suggesting that in this case, as we suggested for the original X-rays changing look AGN, absorption, at least in X-rays, was not responsible for the observed phenomenology. Now, as such, this phenomenology also in the optics is not new, and in fact, disappearing or reappearing broad lines were observed since the early 70s with even the earliest spectroscopy, optical spectroscopy of Cipher galaxies. And in fact, the first object I could find referred in the literature is now almost half a century long, is Markarian 6 that 50 years ago was discovered in 2 separate spectroscopic observations taken 4 years apart to exhibit the reappearance of broad components of the H beta. So this is not at all a new phenomenon. It was not discovered in this century. It's a phenomenon that as such, phenomenologically speaking, was already known at the dawn of the AGN science. But once these quasars, these changing look quasars on relatively quick, fast timescales were discovered, through industry using essentially as a baseline the AGN in Sloan, started in order to identify a sizable sample of the changing look AGN. And this is actually a very complex and painstaking observational efforts, because even if we start with samples of quasars in the Sloan of 100,000 of objects or a million galaxies that are in the large optical samples available now, then you have to follow a certain number of steps before you can qualify a quasar as changing look. And the first thing to do is to identify those objects that exhibit a significant change in the optical flux, because they are the obvious candidate for this kind of phenomenon, but of course that's not sufficient. Then you want to remove a radio loud object in order to avoid looking at blazars. And then, of course, one has to perform the follow-up optical spectroscopy. And this is, of course, the real complex and painstaking things and the real bottleneck. And more often than not, when you starting from 100,000 of quasars in a Sloan sample, one come out just with a few objects that have a changing look phenomenon demonstrated. And nowadays, the sample we can count on is probably of the order of 50 objects overall. Now, I mentioned that for the X-ray changing look AGN, obscuration is very often a reasonable explanation of the apparent phenomenology, but this is not the case for the optically defined changing look AGN. And there are several reasons why variable obscuration cannot be seen responsible of the observed phenomenology. Probably the most convincing one is that whenever one tries to correct for reddening the UV continuum and apply the same reddening to the broad lines in order to see if their disappearance can be explained by differential reddening, simply this model does not work. So one would have to imply a reddening which is different from the UV continuum and the broad lines, which starts already being contrived from a geometrical point of view. But in addition to that, the change in look AGN show large mid-infrared variability, which, if due to reprocessing, implies an even larger optical dynamical range, which is not observed. Estimated crossing times for cloud coverings, at that point, even the torus, because of course you have to explain also the mid-infrared variability, are simply too long with respect to the observed time scale of the changes. And last but not least, the change in look AGN do not show high optical polarization. And this is expected if the main driver of the variability is an obscuration event, as we observe in X-rays. Also, reprocessing is actually unlikely as an explanation, because we see whenever we have a multi-wavelength observation covering optical, UV, and X-rays, for instance, we see that the dynamical range of the X-ray variability is of the same order of the change of the continuum flux in the UV. And that's, of course, something that you do not expect if the variability is driven by reprocessing of the flash of a decrease of X-ray radiation. I think one of the objects that eventually led to a breakthrough, a conclusive breakthrough on this field is the discovery of a changing look in the making, which is the object whose light curve, whose spectra, time-resolved spectra, I'm showing on the right side of this slide. This is an object where actually the changing look phenomenon could be actually seen while developing. So we saw, well, they saw an object for which first one see an increase of the UV flux, and with the delay of 2 or 3 months following the increase of a UV flux, a broad component of the H-alpha line appears. So this is obviously some phenomenon that cannot be explained just with simple obscuration, and therefore requires a phenomenon that probably justification and interpretation that needs a change, most likely a change in the accretion rate of this object. Increasing the ionizing flux, the continuous ionizing flux seen by the gas in the broadline region, and letting the broadline region respond with a delay, which is probably indicative of a light crossing time between the UV ionizing source and the broadline region location. Now, a question that we should ask is whether changing look AGN is an extraordinary phenomenon characterizing a new class of AGN, or it's simply an extreme manifestation of the fact that AGN are variable and are variable at all wavelengths at different timescales. And systematic studies comparing the properties of changing look AGN with the general property of variable AGN in the optical ultraviolet suggest that we are not looking actually at a different phenomenology, but changing look AGN are simply an extreme tail of a distribution of variable quasars. And probably from my perspective, the most convincing element in favor of this hypothesis is that when we look at variable quasars in the optical, we see a anti-correlation between the dynamical range of a variability expressed, for instance, in terms of the maximum continuum variability in a band, and the Eddington ratio. So object with a lower Eddington ratio shows the most extreme variability in the UV. Actually, it's the other way around. Most extreme variable object in the optical UV, they are typically low Eddington. And also changing look AGN are low Eddington rate object, or the Eddington rate quasars. So this points to the fact that changing look AGN are just an extreme manifestation of the general variability properties that we observe in quasars. And this variability is once again due to something that affects the accretion rate in the disk. Now, this is a serious problem for accretion disk models. And why is that? The reason is, as I mentioned, rapid and extreme variability in X-rays and UV is extremely common in the AGN. It's associated to the inner region of the accretion disk or to relativistic outflows. General relativity effects amplify the variability dynamical range through, for instance, light bending, of which, of course, Giovanni could talk very extensively. All in all, this rapid variability can fit the paradigm of the standard accretion disk models. But when we extend this extreme variability regime to the optical band, we are considering regions in the accretion disk of the order of 100 gravitational radii. And this leads to what Andy Lawrence, in a famous short note recently on Nature Astronomy, dubbed as the quasar viscosity crisis. So if the time scale that is relevant is a time scale, a viscous time scale, which essentially sets the diffusion of matter in the accretion disk due to the viscosity, these time scales are of the order of 100 years. And therefore, they don't match the observed variability time scales that we see in the data that are of the order of a few years, or in the most extreme case of just a few months. So what I've said so far, I think it's uncontroversial between Giovanni and myself. So I think on this, I don't think there will be any blood we can shed. So let me now show my blood challenge for today. My blood challenge for today is that I declare that changing look AGN lead us to abandon the hope that the transfer of angular momentum, the generation of heat, and the re-radiation of it can be approximated by a local process. And this is not my words. These are words that I have extracted because I think they summarize very well the key questions or the key challenge I would like to propose for today. And they were expressed in this note by Andy Lawrence I mentioned before, where he mentioned the quasar viscosity crisis. So the solution that my champion is going to support today is that we need actually to recur to large-scale magnetic field supporting the disk vertical structure, and therefore preventing the conversion of gravitational rate into heat and the transfer of angular momentum to happen locally. Now, one of the models that have been put forward in order to support this kind of scenario are the so-called magnetically elevated disk models. These are essentially models of accretion disk where the vertical structure pressure is supported by a toroidal magnetic field. Originally, these models were introduced a few years ago by Begelman and his group, as his collaborators, to explain state transitions in X-ray binaries. But a few years later, they were extended to AGN, and they actually were shown to produce a naturally thickened accretion disk with an aspect ratio larger than 0.1. So why is the aspect ratio key in this context? Because, as we say, the viscous time are too slow, but they have the properties of depending as the inverse square of the aspect ratio in the accretion disk. And therefore, if I have a way to puff up the disk, I can reduce the viscous time scale, making actually the inflow time of matters at the size of 100 gravitational wave radius consistent with the observed time scale of the changing look phenomenon. Now, in a recent paper, Dexter and Bellingham propose different mechanism by which actually a magnetic disk can lead to a decrease of the viscose of the inflow time. They also consider a solution where the disk can be puffed up by the UV opacity or a line-driven wind, and they actually demonstrate that this doesn't work because essentially this opacity is efficient only up to a certain radius, and before that beyond that, actually, this mechanism is not sufficiently efficient in order to ensure maintaining the disk sufficiently large at the spatial scale that we need. Also, local mechanisms where essentially you have a non-zero magnetic torque and in the edge are helps, but they are insufficient in order to decrease the inflow time. So what they show, of course, in support of their own model, is that this kind of magnetically supported disk or magnetically elevated disk, which are shown by the cyan or light blue curve in this inflow time versus radius plot, they actually create naturally this high aspect ratios disk that actually can decrease the inflow time, the viscose time, up to the level to be compatible with a few years or even a few months time scale that we observe in the data of changing look AGN. Now, but there is not only optical UV in changing look AGN to look after. A recent case, the same case I was showing before of the changing look in the making, was also heavily, intensively monitoring in X-rays, and it shows a remarkable variability of the corona emission, the X-ray emission, decreasing by a factor of 2 orders of magnitudes in a few hundred days, and then recovering to a level which is actually higher than the level of the quiescent the normal accretion state prior to the changing look event. Now, this is of course adds an additional degrees of freedom to be explained by these models, and the most recent incarnation of the explanation in terms of magnetically sustained disk are the so-called magnetically arrested disk. In this case, these are a disk where there is an accumulation of magnetic flux in the innermost region of the disk due to ram pressure from the accreting matter. And these disks yields naturally 2 important properties that characterize changing look AGN during their faint state, which is the relatively low ultraviolet efficiency, because essentially the gravitational power is no longer converted into ether radiation locally, but the magnetic structure of is the global magnetic structure of the disk that mediates the conversion of gravitational energy into heat and radiation. And another properties of this disk is that they, when you have for whatever reason a mechanism whereby a field of a different polarity is actually driven through the center by the accretion rate, you can create changes of polarity because the opposite polarity accretion disk from the outwards to inwards annihilated the pre-existing large scale toroidal magnetic field, and this creates at some point a depression, a disappearance of the corona, and this disappearance of a corona occurs after the increase of the UV emission, because essentially once the disk is no longer magnetically supported in the other ratios, it becomes more efficiency in the UV. And once the polarity is completely inverted, at that point, a magnetically arrested disk can be recreated with an inverted polarity, creating once again a corona, and the polarity of the disk is irrelevant as far as the phenomenology of the corona is concerned, and also a recovery of the situation whereby the UV efficiency decreases, and therefore you should see on one side a recovery of the X-ray flux as observed before the changing look episode, and then a decreasing UV magnitude, which is exactly what the data suggested. In this case, in the panel in the left side, the UV magnitude is showed in the bottom panel, which is instead decreasing where the X-ray corona is doing first the dimming and then the recovery. So this is the end of my part. As said, I remember, you know, to recall my opponent, that's the challenge that I am putting forward, and now I am challenging my opponent to demonstrate that actually this hypothesis is untenable. Giovanni, floor is yours.
Thank you,
First,
Matteo.
Francesca.
Yes, thanks, Matteo. So the opponent is Giovanni Miniutti. Giovanni got his PhD in La Sapienza University in Rome, and then he moved to the Institute of Astronomy in Cambridge, working with the X-ray group for 5 years. And then he went to Paris for a year as a staff researcher. Finally, he got a Ramón y Cajal Fellowship in Spain at the Centro de Astrobiologia, where he's actually a staff member. So Giovanni, please reply to Matteo.
So let's see. Can you see the presentation?
Yes.
Yes. Okay, fine. So just to finish exactly where Matteo, to start exactly where Matteo finished, I'm also, I don't know if I'm asking the help of some medieval expert or if I'm just exposing myself together with my collaborators. So let's first start. I cannot change. Okay, so let's first start. Sorry, but I have a few things that are coming up. Okay, so let's first ask why are these objects so interesting? So obviously, changinglook AGN are probing a new territory. They, as Matteo explained, they challenge our understanding of the accretion flow and of the how gravitational energy is converted into radiation, and they probe phenomena on time scale that so far we have only probed through a population study, assuming some evolution. So you get a sample of AGN with different property, and you can study their different physical states. But without no information on how to go from one state to the other exactly. In this case, a bit like in X-ray binaries, changinglook AGN are providing a possibility to probe different physical states, most likely related to accretion rates, on human time scale of months to years. So this is something that is unprecedented in the AGN community. And they because of this, they provide a tool, a unique probe for theoretical models and the associated phenomenology. For instance, they can probe accretion states. Difference in mass accretion rate in X-ray binaries we know are associated with the state transitions between soft disk-dominated states to hard, let's say, Comptonization dominated or jet dominated states when the mass accretion rate drops. And we have an opportunity to study the same kind of phenomena here in AGN for the first time. Another thing that we can study, of course, is the actual accretion geometry at different mass accretion rates. So now we are. I'm showing here an example by Stefano that is not related directly to changinglook AGN, but shows that with a suitable set of observations, you can probe the accretion state geometry in the very low mass accretion rate end, as is this case, where Stefano was able to show that actually a geometrically thin, optically thick disk exists at relatively small radii, even in the case of very low mass accretion rates. So imagine if you can do that and follow that in a single source over the course of a few months or few years, you could probe the geometry and the evolving geometry of the accretion flow directly with this kind of observations. And of course, we can also probe the broadline region, the broad emission line, the optical broad emission line formation, origin, location, and evolution as a function of source property. In this particular example by Fabrizio, he predicted a given functional form for the full width and maximum evolution as a function of accretion rate, which can now, for the first time, be probed thanks to changing look AGN that evolve through different mass accretion rate. A single source, you can check this kind of predictions and make your models accordingly. So as mentioned by Matteo, changing look AGN are a rather complex two-way phenomenon. So we don't see just the turn on AGN or turn off AGN. We see the build-up of the optical broad emission lines as well as their dimming, associated together with generally associated with an accompanying variability in the optical UV continuum. What I think it's particularly interesting, and that has not been mentioned so far by Matteo, is that sometimes some of these sources do both things. So they turn on and start to build broad optical emission lines. They stay active, let's say, in a type 1 AGN style for a few years or decades, and then they dim back again to, let's say, quiescence, where the broad lines are not there, or at least very difficult to see due to host galaxy contamination, as Stefano showed for the case of this very low mass accretion rate object. Interestingly, these sources, there are sources that do that repeatedly. For instance, in this case, you see Markarian 590 that built it up since the 70s, its broadline region, and then went back to a CIFER2 like optical spectrum, and is now, since a few years, reawakening, and broad lines have been detected again. So this kind of repeated oscillations may tell us something about that. That may justify the fact that we are maybe not looking at the standard variability in the optical, but as something that that occurs in a recurrent way, that we are able to look as a repeated event just in a few sources where timescales are particularly short. So just to make an example, this is the case of Markarian 1018, who had a transition from type 2 to type 1 in the 80s, and then a transition back to type 2 in 2010, and lasted a few years. The last decay, since it was in 2010, has been monitored in the X-rays and in the optical UV through SWIFT and XMM, so it's rather well monitored. So Node and Dawn, I've presented some results about the decay of these sources, and here you see a few spectral energy distribution to say what's the overall evolution of the source during these 6-8 years of the decay that is accompanied as well by the disappearance of the broad optical emission lines. So basically, you can see from that figure that from the high to the low flux states, the hard X-ray drop is about a factor of 6 or 7, while the UV dropped by a factor of 20. And most importantly, the soft excess component in this source drops by at least a factor of 60, maybe completely disappears in the low flux state. So basically, during this decay, the source loses the soft excess. And the argument of Node and Dawn is that since this component is likely to contribute the most, or at least very, very significantly to the extreme UV emission, this may be driving the BLR response. So basically, the disappearing of the soft excess is directly responsible for the disappearance of the broad line. This is an example. This is, well, the spectral energy distribution at different flux levels. So this you see on the left-hand side the light curve of the source going down back to quiescence starting from 2010. And you see on the right-hand side here the spectral energy distribution. Here is the host galaxy contribution, the accretion disk in the high state, a huge soft excess. The soft excess goes down and basically disappears in the low flux state. So this is, if you compare the spectral energy distribution of this source from the high to the low state, this is remarkably similar to what galactic black hole binaries do in state transitions. So when they go from the soft disk-dominated state to the hard, let's say, comptonization dominated state during an outburst, at the end of the outburst. So this suggests that changing look AGN, and in particular in this case, but more generally changing look AGN, are experiencing state transitions. And so they will not be, or at least a large fraction of them will not be just an extreme tail of the standard variability, as Matteo said, but will be associated with spectral transition, very similar to what is seen in X-ray binaries during transient outbursts. To be a little bit more quantitative in this analogy, Sobolewski et al. In 2011 have done an interesting work, in my opinion, comparing, trying to extrapolate from the behavior of X-ray binaries in outbursts, what will be the observational signature of AGN experiencing similar outbursts, of course, on much longer time scales in principle. So what they did is they tried to define first an equivalent alpha OX, so the spectral slope from the optical to the X-rays for X-ray binaries, in the sense, of course, X-ray binaries have both the disk and the comptonization component confined into the X-ray regime, so you have to define things in the X-ray band, and you can define an alpha OX, an equivalent alpha OX that describes the evolution of the X-ray binary during the outbursts as an AGN will do with the alpha X from optical to X-ray. Then they have considered one particular case that is well monitored and well studied, and they took the outburst of these X-ray binaries, modeled with a model that could be, with some caveats, extrapolated to AGN, taking into account the different black hole mass and so on. And then they consider a population of AGN. Let's say, look at the sample at Cosmos survey, for instance. I think it was in this case. Extrapolate the mass distribution and so on, and see what will be the observational signature of AGN doing similar outbursts that are based on the evolution of this particular X-ray binaries. So basically, they build a spectral energy distribution for AGN in the soft and hard states, and then draw from probability distribution, the probability of an AGN being soft and hard and with some kind of parameters, and try to see what will be for instance, one of the things that they try to see, what will be the behavior of alpha OX for AGN as a function of editor ratio. And so what they found is the standard, let's correlation between alpha OX and editor ratio, that then below a few percent of the editor ratio turns up and becomes an inverted correlation. So basically, they would suggest that if AGN share similar spectral properties of galactic black holes and experience outbursts that can be described by extrapolating and by let's say stretching in some sense the SCD and the time scales of galactic black hole binaries to the AGN population, you would be able to see this kind of inverted profile in the alpha X versus editor ratio plot. Let's say the spread here is basically due to the different mass of the black holes that they consider in their distribution. In fact, as Ruan et al. In 2019 have done, they have observed the changing look AGN with Chandra when basically after fading, so in the low state, to look for this possible anti-correlation between the UV to X-ray spectral index, the alpha X, and the editor ratio. And what they found is, in fact, that their results seem to suggest that there is, in fact, an inverted profile, an inverted correlation there that is obtained for AGN that in this view would be in the hard state and at very low Eddington ratio. Below a certain Eddington ratio that is a few percent as predicted from AGNXIV binaries. And in fact, if they look at the same change-look AGN, but just before fading, they see that they sort of, although there are lots of limits there, that they sort of recover the correlation. So it looks like that similar accretion geometries and evolution could be present in both AGN and X-ray binaries, and that the transition luminosity that is known for X-ray binaries to happen at a few percent, at least in the decay phase, similar transition luminosity in terms of Eddington is present also for AGN. So this strongly suggests that state transition are taking place there in strong analogy with what X-ray binaries do during outbursts. So the fact that there are repeating changing look AGN, so we know that X-ray binary outbursts are repeating, of course. And the analogy between the spectral transition Eddington ratio suggests that perhaps AGN do the same. And this was actually what was proposed by Noda and Dawn in their paper on Markarian 1018. So they tried to see whether what they identify spectrally as a state transition in Markarian 1018, going from the soft high to the low hard state, can be reconciled with the same mechanisms with which X-ray binaries are known to go into outbursts, which is an instability associated with the ionization of hydrogen, as in dwarf novae. X-ray binary and dwarf novae share the same mechanism for the outburst generation. In this case, well, basically, you start from the outer disk, you start to ionize hydrogen. As locally the hydrogen becomes fully ionized, there is a jump in temperature, so a jump in sound speed. You propagate this faster, the mass accretion rate, and basically you generate the outburst. And the propagation time scale for this is not the viscous time scale. It's actually faster by a factor of R over H than the viscous time scale. And if you just translate the time scale of dwarf novae or X-ray binaries to AGN, taking into account not only the mass difference, but also the location of this unstable region that is much, much closer in AGN because of the colder disk than in X-ray binaries, you end up with timescales that are not quite right. So they are not of the order of months to years, but they are not far off. It's not 10 to the 5 or 10 to the 6 year as would be the viscous timescales. And this is confirmed also by numerical simulation of this kind of ionization instability in AGN that have been performed by Emery et al. In 2009. However, these simulations are done ignoring the fact that the inner part of the accretion disk in AGN, unlike X-ray binaries, is likely to be radiation pressure dominated, and even more so, even unstable to radiation pressure instabilities. And this is not included in the simulation. Of course, radiation pressure will increase the sound speeds again of the inner flow, and so it may be sufficient to reduce the time scale to the observed months to years time scale observed in changing look AGN. Unfortunately, no blood here, because as my opponent proposes, magnetic support is an alternative. Of course, it can increase the thickness of the accretion flow, so the aspect size of the accretion flow, thus reducing again the time scales. One final thing I want to mention is that relatively toy model simulation have been started to be performed in this context, based not on the ionization, hydrogen ionization instability, as I said before, but on the radiation pressure instability. There is a long story of a simulation of this kind. And in this kind of toy model proposed by Senegovska, Czerny et al., they consider an inner IDAF a very small unstable disk surrounded by a stable disk. And what they found is that if the stable disk is sufficiently small, the unstable region is sufficiently thin, so basically a narrow ring, they can indeed reproduce timescales that are commensurate with observation. So if you see here these outbursts that are of course repeating, its limit cycle oscillation as in standard radiation pressure instability recur every few tens of years or so, and the duration is much smaller than that, so of the order of years. And the decay and the rise as well, of course, they are much smaller. I didn't go too much into the details of that. I think that this is basically an artifact of having a very small unstable region is what allows the fast propagation of perturbations there, and therefore the onset of the instability on very short time scales, but it's a promising possibility to explore, of course. A final thing I wanted to mention that is related to that is the observation of this quasar, where both the UV continuum and the broadline region have faded and returned over the course of 20 years, so another, let's say, repeating one. And here what I show are the optical UV spectra that have been taken, and you can see a difference, important difference between the, I have to take that away, sorry, between the blue, green, and black spectra and the red one. That has been modeled, that has been modeled in terms of non-zero torque boundary condition at the ISCO for the accretion disk in the case of the upper, let's say, spectra, the blue, green, and black, which is something that Matteo mentioned before. So basically, you imagine that there is a magnetic field threading and connecting the inner accretion disk with the plunging region close to the black hole, and this produces a torque, and this torque puffs up the inner part of the disk, and that becomes more UV luminous, and so this is why you get this kind of spectra here, and this model is just a disk with non-zero torque. But then some event, probably the redistribution of this mysterious magnetic field, deflates the inner disk to zero torque and produce some transient cold absorption, which may be actually the disk, the puffed up disk that collapses and leaves some clouds for a transient period. And this is what this red curve is. Basically, you have a non-zero torque disk plus some cold absorption. And this led these authors to speculate together as well to further photometric data that they had, a phenomenological picture for these sources that has some resemblance with what I was talking about, in the sense that you start with a puffed up disk in the inner region, some triggering event reduces, eliminates the non-zero torque boundary condition and creates a zero torque, so standard Shakura-Suneave disk in the inner region. And this basically produces a front that propagates outwards, a cold front that propagates outwards, and then is followed by a hot front that propagates inwards. That is exactly what happens in the ionization, the hydrogen ionization instability in outbursts. So you have these fronts that propagate. Again, the propagation speed or time scale is the same as I said before, R over H shorter than the viscous time scale. And so again, you are in a similar situation. You are quite right with the time scales, but not exactly. So you need still some extra component to be able to reduce the time scale further. Now, in the propagation, in the outward propagation, we are propagating in the puffed up disk, so it's okay that you get an H over R that is it's a bit higher than standard. But definitely not in the other way around, because when you propagate inwards, you are propagating into optically thick, geometrically thin disk, and their time scales must be greater. So, in response to my opponent idea, I declare that the repeating changing look phenomenon, the fact that changing looks AGN are repeating often, not always, but in some instances are repeating, And the fact, the apparent analogy with X-ray binaries, spectral transition at exactly the same L over LED of a few percent, which is, by the way, where changing look AGN are seen. This call for a solution in terms of state transition in changing look AGN rather than a tail of the standard variability. And this spectral transition may be driven by instabilities. Timescale are then set by the propagation of the fronts rather than the viscous timescales. This is shorter, but not quite enough. So the inclusion of radiation pressure may increase enough the sound speed. You need to simulate, for instance, the disk hydrogen ionization instability that give rise to the outburst in X-ray binaries and possibly in AGN, but with much longer timescales, together with the proper description of the inner disk to see if the timescale can be reduced sensibly. Also, this is difficult to do because the inner part of the disk is thermally unstable because of radiation pressure instability, the limit cycle oscillation due to radiation pressure instability. So things that have to be explored are the fact that corone, both the standard contonization, optically thin corona, and that possibly producing the soft excess, which would be warm and optically thick, or winds and outflows may help stabilize the inner disk. And so in this sense, you will have the radiation pressure support, which may speed up the process, but without the instability. So these are things that may be worth considering for understanding what's going on in these sources. But my point is that it looks from a different points of view that changing look AGN are tracking X-ray binaries outburst in their evolution. However, we must be careful about pushing too much the analogies. Here I show a recent work that we have produced where we have seen quasi-periodic abrupt variation in the X-ray band in a likely tidal disruption event, following a likely tidal disruption event. Now, these things have been observed in other sources, very similar to that one, so things that are most likely tidal disruption events. And in fact, if you look at the property of this kind of outburst, these are very similar to what we have seen for changing look AGN. So here what you see is the profile of one peak. It's actually the folded profile of our peaks. And you see the spectral evolution. So you start with what can be described as a cold accretion disk, standard disk, and you build up what is very, 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 very similar to a soft excess. Same temperatures, you can describe the data exactly in the same way as you describe a standard AGN soft excess. And in the decay, you lose the soft excess, basically. You simply return to the AGN disk. So very similar behavior as Markarian 1018, with a spectral X-ray component that strongly resembles the soft excess that fades away during the decay. On the other hand, it's not exactly the same because the low flux level, the quiescent level, is rather called the standard disk, a radially efficient disk, not a state transition like in Markarian 1018. Even considering the very likely small black hole mass in these sources, radiation pressure instabilities that have been simulated to explain this behavior cannot do that, cannot cope with 9-hour separation between outbursts, even if the black hole mass is small, and burst duration of just 1 hour. And in fact, the arrival time of these outbursts are more consistent with orbital motion. For instance, impact of a black hole or of a star on the accretion disk surrounding the black hole may give rise to outbursts each time they cross the accretion disk with a mechanism that is not entirely clear, but this is possible. And to conclude, a recoiling supermassive black hole has been proposed as a possible explanation of Markarian 1018. So no state transition, no accretion flow instabilities, no magnetically supported disk, although some sort of accretion change must occur in this case, but just a recoiling black hole the product of a possible likely merger, that oscillates around the center of the galaxy and gets accretion enhanced every time at periastron passage. So my real challenge is, well, I guess that you can get it from that look and grimace. I have more questions than answers. Thank you.
Grazie, Giovanni. Thank you, Giovanni. Okay, I think this was very, very interesting. It poses a lot of questions, and to make an analogy, I think we are starting to leave the medieval era of considering AGN as a static picture. They're more very, very dynamic systems like X-ray binaries, but the things are complicated by the interactions with recoiling black holes being in the galaxy. So the picture is much more complicated. But Changing Look are offering, I think, a good opportunity to investigate the dynamic of the nuclear region of the AGN. So I think it's time to accept questions, and please raise your hand if you want to pose questions to Giovanni and Matteo. Yes, I see one. Fabrizio, of course.
Of course. Can you hear me?
Yes.
Okay. Very interesting talks, both. I have a few comments and questions related, but not particularly to the speakers, I mean, to all of us. Well, first of all, I don't understand where the controversy is between the two speakers, because essentially they both agree that as a general point, there must be some sort of state transition which is related to the accretion. Besides, I mean, events like quasi-periodic oscillation, which are due to stochastic phenomena that may always be there. But in general, there must be some analogy with the X-ray binaries. And we know that those objects make transitions due to difference in the accretion, essentially. In our paper, but the point I would like to make is that the two things, the two views from Matteo and Giovanni, I think must be merged somehow, because there must be, I think we cannot avoid the viscosity time scale, because if we only look at instability as far as emission, continuum emission is concerned, then yes, I mean, you can also avoid probably, as Giovanni showed, viscosity instability. But another very important piece of information we have from AGN and not from X-ray binaries is the broad emission lines. In broad emission lines, you have to physically move material from one side to the other. There is no other way around, unless you believe that the Laur model is correct. But it has been there are clear evidence that this is not true. I mean, the luminosity, only the luminosity cannot, I mean, these things don't change as the root square of the luminosity. The width of the broad emission line region and the position, the location on which these broad emission line region are emitted. This has been clear already since the Caspi paper of
Fabrizio, when you say Laur, is the idea that the brown light region are essentially the sublimation radius of the dust? That's what you want to say, or it's another theory?
I mean simply that they scale as the root square of the luminosity because of ionization reason. I mean, you can only photoionize, you can only see what you photoionize at the right level of photoionization. And this is due to, of course, a ratio between the luminosity of the ionizing luminosity and the distance at which you produce this line. But it doesn't go that way. I mean, it was already clear in the Caspi reverberation paper on quasars that the scaling is roughly with a power of 0.75 and not 0.5, and it's not a matter of, and this has been more or less confirmed by other experiments later. There is also, we never wrote a paper on Macarian 509 or 590, I don't remember, but even there you can clearly demonstrate that simple picture doesn't work. So and instead this 0.75 power comes naturally from instability in the disk, particularly at the radius of the where you have the radiation pressure dominated and the gas pressure dominated transition region, which is what also Bocena-Chersny in her models, all her models since 30 years now, try to demonstrate. We also have these, our model of 2000 is also on the same line. So I think we must reduce some, but the viscosity instability, as you both say, is way too long for these transitions that we observe, that are of the order, time scales are of the orders of tens of years, 30 years, 40 years, whatever. And the other thing, the other comment I want to make, Giovanni, you mentioned that we only see these in the AGN in which we can see these. I think this is partly correct, and it probably depends on the mass of the AGN. But we also have to say that we only see these now because we only now have covered with observations at times to see this.
Yes, I mean, yes, true.
Observations of broad emission lines and AGN and Stephens are now 30, 40 years old. And so we start to see these things. So, I mean, yeah, essentially mine is a comment. We have to find a way of reducing this viscosity time scale. The other thing I want to add is that H over R is important because it goes as the square to the -2, but there is also alpha, and this viscosity prescription is completely unknown. We consider it constant, but it doesn't have to be with a radius, and most likely it's not. I mean, well, there is no reason why the viscosity in the disk is the same at the transition radius between gas pressure and radiation pressure dominated and at the ionization radius of the hydrogen, which is far, far away from there. It must be different. It is probably very different. But even if you don't consider it, even if you consider it constant, it may be bigger than we assume. If it is 0.5 rather than 0.1 or 0.05, you already gain a factor of 5 to 10.
Yes, it's a linear dependence, so it's not as the aspect ratio. But yes, you're right in principle.
So it can very well be a combination of H over R, alpha, or whatever. But I think we cannot avoid the viscosity time scale. And I stop here.
Do you want to comment on the comment or?
No, the only thing I'm Giovanni. The only thing I agree with, not the only thing I agree with, but I certainly agree with the fact that there was not too much blood between Matteo and I, in the sense that we both agreed, I think, that we need to reduce these time scales by either increasing the aspect ratio of the disk somehow, but without losing all the successes of the Shakura-Sunyaev description for the emission. And definitely his conclusion that the Dexter and Begelman model might be consistent with data, it's difficult to counteract, in the sense it's definitely a good idea and it's a possibility. The problem is trying to make general statements and arguments when you touch such mysterious things are magnetic fields, global magnetic fields. It's difficult, but it's the same for instabilities where numerical simulation are the only way forward. So stop here.
Yeah, no, it's just a small further comment. Fabrizio, of course, is right when he says that we both agree that the changing loop transition is, we both agree that is related to an accretion, and you know, I don't think this is controversial. In fact, it's simply suggested by the data that tell you the changing loop AGN, they are low accretion rate objects. So I think the key question from my perspective is, are changing look AGN low accretion objects because the fact that they are low accretion object as normal variable quasars are is just a conspiracy, or it's a coincidence, because in reality changing look AGN are a different kind of beast and might be related, as Giovanni said, to the kind of transition that we see in binary. And that's probably the difference. No, I am, let's say, from a rhetorical point of view, sustaining the idea that they are actually just the same, and Giovanni is rhetorically sustaining the idea that no, they represent a two qualitatively different phenomenology, and the latter can be associated to the binary transitions. I think that's the challenge that we are putting forward.
Okay, there's another question from Alfredo.
Can you hear me?
Yes.
Okay, so I have let's say a question for Giovanni concerning the role of winds and outflows in stabilizing. Since with Andrea Marinucci, we should be also attending the seminar, so if also has something to add to what I'm saying, he's welcome. So we are working on a source which is NGC 2992, which is a, let's say, candidate changing look, showing intermediate behavior from Seifert 1.8 and 1.9 and Seifert 2. And the interesting thing is that we do observe ultra-fast outflows with velocities very high, between 0.2 and 0.4 times the speed of light. And interesting, these UFO features are observed only in high flux states, that is where the luminosity is higher than 1 or 2% the Eddington rate. So I was wondering if this could fit in the what Giovanni was saying regarding the role of winds in stabilizing the structure in changing look objects.
Well, I guess my point was simply the fact that if you want to invoke state transitions in AGN associated with similar mechanisms, as in X-ray binaries, for instance, through the propagation due to the hydrogen ionization instability, you must describe the system as it is. So with a transition between gas and radiation pressure dominance. And at present, this has never been done. In the sense, the only simulation that there are of this kind of instability and therefore possible state transitions in AGN get timescales of the order of 10 to the 4 or 10 to the 5 years for the waiting time between different outbursts, and very long outbursts in any case, even the duration of the outburst. But do not consider the fact that the inner part of the inner region of the disk is radiation pressure dominated. Why? Because this is unstable. So you are getting variable fast mass accretion rate from outside because of the hydrogen ionization instability. You are unstable in that region. This is impossible to treat, basically. But possibly the role of any kind of outflow, I'm not particularly suggesting UFOs, any kind of outflows, possibly the most energetic ones are more important, may, just by removing mass from the system, may be able to stabilize that region, and then preserving the shortening of timescales due to the fact that the region is radiation pressure dominated, so the sound speed is higher and so on, may enable the system to go through and conclude the spectral transition initiated farther out in the disk. That's all I wanted to say.
Okay, thank you very much. Okay.
I see Guido also has a question.
Thank you. I have just a comment. I just wanted to add another piece to the puzzle. I think we shouldn't forget that another physical process that should be included in the overall explanation is the fact that the X-ray emission either variable or not, but is persistent, and so there must be something which refurbish the X-ray emitting corona from an energy point of view. So maybe the global magnetic fields that are invoked by Fabrizio could be a way also to somehow transfer energy from the disk to the corona or something like that. And even regarding the analogy with binaries, I think that this is also in this case, this is a crucial point, because it's true that the hard component in the emission of binaries is similar somehow to the AGN emission, but the disk emission is of course completely different because the temperature is completely different. And so I think if there is a strong analogy, we should also think about how the way to transfer energy to the corona is the same in both classes, even if the disk, which should be where the gravitational energy is released, is so different in the two cases. So, what do you think about that?
May I start, Giovanni?
Yes.
Yeah, just saying that I agree with Giovanni, and indeed the model that I was showing here, maybe I was a bit too fast, shows, in this slide you see on the left side is the X-ray light curve in the top panel. And on the right side of the slide, the upper panel is, let's say, a cartoon prediction of how the X-ray light curve should behave. That, of course, is aimed to reproduce, at least in a qualitative term, the observed data. And the idea here is exactly that once you have this phenomenon leading to the change of polarity of the large scale toroidal field, at the beginning, what you are doing, you are essentially destroying the magnetic field with the original orientation. And by doing that, you are also destroying the corona that is magnetically supported. And then the corona can reform only once a new large scale toroidal field with an opposite polarity is actually started to reform. So you can make with the model that I showed in my last slide, semi-quantitative predictions on the evolution of the X-ray light curve. And in fact, it goes actually one step beyond, because this model makes also, some sort of semi-quantitative prediction on the ratio between the level of X-rays that you reach after a changing look event and the level of X-ray flux prior to the changing look events, depending essentially on the ratio between the Eddington ratio before and afterwards, and depending also on the relative efficiency in radiation emission between X-rays and UV. There are lots of details, of course, that goes beyond my explanation and probably also beyond my understanding, but the model is intended indeed to provide at least a semi-quantitative explanation of the X-ray light curve, although it recognizes that it cannot in detail yet explain the X-ray spectral behavior, because we also see in this specific event, a hardening of the spectrum during the changing look event that cannot be yet clearly explained by the model.
Okay, Giovanni, would you like to add something, or?
No, I'm not too familiar with that model, so I trust Matteo on this. The only thing I can say about Guido's comment is that when Sobolewska et al. Have tried to to predict what the AGN state transition would look like, it is obviously true that the disks are different. One is hot, one is cold, etc. But they basically described the AGN SCD based on the XRB's SCD by assuming the same share between the power that goes into the seed photons and the power that goes into the hot corona, the hot electrons. This was the main assumption for stretching the galactic black hole binary X-ray only SED to the optical UV X-ray SED of AGN in state transitions. That's all.
Can I add something to this very quickly?
Yes, go ahead.
Yes, and this was also what you just said, Giovanni, was also present in the model by Witt, Chesney, and I don't remember what was the third author of that paper in the 90s, in which they do exactly this. They use a corona to stabilize the radiation pressure dominated region, but for the first time, they use a co-accreting corona, which is reasonable to do. I mean, there is no reason why the corona should be static and the disk accrete. And these generate through the power, they study the power which is diffused into the wind. They say that at some point in the corona, in the disk must be launched the wind, because this power, which is now I cannot find the word in English, but dissipated in the wind, is maximum. And at their radius, you must have the launch of a wind or some expelling material from the disk somehow vertically. And this is a way to also to come to the comment of Guido, to transfer energy into the corona. So by just co-accreting, letting the corona co-accrete with the disk, you find these solutions. And this was already present in the 90s.
Okay.
Francesca, I am allowed to strike a blow to my opponent.
Yes, of course.
Well, listening to Giovanni's presentation, I was curious, since if changing look AGN are the analogous of state transition in binaries, do you expect to observe also changing look AGN transitioning from radio quiet to radio loud states?
As I said in the last slide, we shouldn't take the analogy too far, but because it's just an analogy. So I was driven mostly by the fact that these results of changing look AGN by Ruan in 2019, showing this inverted alpha X L Eddington relation for faded away changing look AGN, to build up an analogy for this part, which is the state transition. Then, frankly speaking, I'm not an expert on blob ejection and so on in X-ray binaries to know what the mechanism is and if it can be translated. I guess that people have done, people who have built HID diagrams for AGN have shown that the clustering of radio loud objects is more or less in the right place. But that's all I can say. And true, what you are saying is that since the time scales for changing look AGN are immensely shorter than expected with respect to X-ray binary, so it's not just a scaling relation, then you might be able to expect reactivated radioactivity in just a few years or even less, because in binaries the ejection is very short in time. So you are right, but I have no answer to that. It may be a possible consequence if the analogy holds, but I don't know if it holds or not.
Matteo, can I say something about it?
You give the answer or either now or in 3 days when you have published the paper. Go ahead, Francesca, of course, you're the chair.
Well, this is also, I think, the part of the ejection is a very crucial point, as it is in X-ray binaries is completely connected. No, when you transit from one state to another, there's a change also in the radio part and the injection of jets. And for AGN, of course, the situation is very complicated because you have different classes of radio loud AGN, young radio loud, radio quiet, and radio galaxies. And you start to see finally the radio galaxies that are changing look. I mean, they are switched off and switched on in their jet activity. So you can start, thanks to LOFAR and all these new results, you can start to estimate duty cycle of the jet activity. And then you have that information that you can use in your HID diagrams. And that's what, we're doing. But also, when you look at the small time scale for the radio variability, there is very little about this, but we're doing a lot of work on this side. There is variability and there is transition from radio loud to radio quiet on month scales. So this is, this is also very, very new, but it has to be combined with all you have presented today. And to all those UV and X-ray light curves, you should add a radio light curve, I think. By Giovanni.
Are you talking about core radioactivity, right? It's not, you are looking at the cores and see switching it off and on months time scales. Is that?
Yes. Okay. Varying, not switching.
Okay.
Yeah. Okay. Any other comment?
So Francesca gave me just to say that, yeah, I mean, the radio connection may be less visible than others, because that also depends on the kinetic power you are able to input in the material which is expelled in the jet. I mean, you may not get a relativistic jet out of a monster as an AGN compared to an X-ray binary, even if the phenomenon is the same.
But also in X-ray binaries, you don't only see relativistic jets, you see any kind of ejections. I mean, also in this field, you have different flavors, no?
No, but in the state transition, you clearly see a powerful radio source versus a radio quiet. And that has to be due to the jet when the radio power is on.
Yes.
And all I'm saying is that in an object which has 10 to the 6 times the mass of a binary, the kinetic power that you put in the jet may be, or in the wind, may be lower. And so perhaps you don't see this powerful radio emission.
Yeah, I wonder if the model that Matteo has presented about this vertical disk and vertical magnetic field can, help in collimating the flow, for instance.
Okay. Yeah, there are expectations that this large-scale toroidal field can occasionally eject blobs of magnetized plasma, and whether this is a wind, whether this is a jet, I can't tell in this moment. But of course, yes, there has been calculations by Begelman groups on that one can look at more quantitatively. But yes, qualitatively, you expect ejection of magnetized plasma from this large-scale toroidal field.
Okay, so I think this could be a very long discussion. So if we do not have any other questions, we would like to thank the speakers today for your contribution. And I leave speech to Paolo. Paolo, do you have to say something? Announcements?
No, thanks to everybody. It was a very nice start. And so thanks to everybody. We reconvene tomorrow at 3 p.m. I'll circulate the new link soon.
Okay.
So thanks, Matteo. Thanks, Giovanni. Thanks, Francesca.
Thank you.
See you tomorrow.
Thanks for the invitation.
Bye-bye.
Bye.